started in just a minute. Are we okay? All right, so I know it's been a long day, but we've had a lot of incredible talks. To sort of wrap things up here, we're going to have another rapid fire round of some amazing stuff going on throughout the TVM community. And to kick things off, Ed is going to tell us about graph convolutional cost models. Please take it away.
Yeah. Thanks, Zach. So today I'm just going to give a quick look at some graph convolutional cost models that we can use for TVM. And just to give an introduction, one of the nice things about TVM and the project so far is that we've been able to build this automatic optimization system around it. One of the major parts of this automatic optimization system that's been really nice is the cost model that we use to estimate the performance of proposed implementations. However, the cost models that we've used so far have some limitations, despite the fact that currently they work pretty well in practice. And the main limitations of current cost models come in the form of some limitations in their generalizability. So our current cost models have some limited generalization between workloads, for example, convolutions with different shapes. And they also have limited generalization between different computation expressions. And what I mean by different computation expressions are things like a convolution versus a matrix multiply, for example. The fundamental compute expression is different in TVM. And so because of these limitations, our current approach is that every time when we have convolutions of different shapes, for example, we will eventually train a separate cost model. And for different compute expressions, we'll eventually train a separate cost model to handle the tuning for those as well. And all of this extra training of cost models takes time. And so one observation is that part of these limitations comes from the fact that we use feature representations for these cost models that are specific to workloads or to compute expressions. So if we increase the how well the feature representation generalizes, then potentially we can improve how well the cost model is generalized too. And so one possibility here is just to use a graph representation directly. And so the motivation for this is that the TVM IR already gives you some kind of AST that expresses the schedule for a computation. And we can use this AST to directly lower into a graph format that is amenable to a graph convolutional neural network, for example. And just to convince you that this can make sense, this is kind of a very simplified AST that has a few variables that compute an expression. And even in this undirected graph format, you can see that it already encodes basic properties of schedules that we're interested in, like the loop ordering. So if we permute this loop ordering, then it's captured in the graph representation. And the way that would work is the expression would be kind of the child of a different for loop in that case. And so in practice, the graphs that we have in TVM are a lot larger. They are on the order of about 1,000 nodes or so for every schedule. But this is still kind of within the realm of possibility of things that you can regress or classify with graph convolutional neural networks. So to summarize and to finish things off, I'll just show some early results on graph convolutional models compared to existing TVM baselines on estimating the performance of some workloads in resonating. So here on the y-axis, we just show the mean squared error of the estimated performance. And the x-axis is the different tuning tasks for a resonating workload on a GPU. And so we can see that the graph convolutional methods, those are the red and green ones, can improve on the baselines in this example. And so the next things we want to look at are improving some metrics that are more directly relevant to TVM tuning tasks, such as like the top K recall and how well transfer learning actually happens between different workloads. Thank you. That's it for my talk. Yeah.
Thanks, Eddie. And I think, like lunch, what we'll do is sort of hold questions till the social gathering after the session. Is Eunji here? Oh, perfect. Okay. And up next, we're going to hear about Janus? 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 Okay.
Yeah, Hello everyone, I'm Eunji from Seoul National University. Today I'd like to introduce Janus, a system that unifies two distinct paradigms in deep learning frameworks to achieve programmability and performance at the same time. This is a joint work with my colleagues and my advisor, Professor Byung-gun. Recent deep learning frameworks can be classified into two categories, symbolic and imperative, based on how the frameworks represent and execute the computation. In symbolic deep learning frameworks, users first build symbolic data flow graphs, and then the graph is executed later separately. On the other hand, in imperative deep learning frameworks, the computation is directly executed. Each of the framework has its own advantage and limitation. In terms of performance, optimizing symbolic graphs is easier than optimizing imperative programs, and in terms of programmability, however, imperative programs are much easier to write or debug compared to the symbolic graphs. Our motivation is to unify two paradigms to make deep learning easier and faster. Janus tries to combine the advantages of each approach by transparently converting imperative programs into symbolic graphs. Here we have a challenge, however. The conversion process is not trivial when we consider imperative programs written in Python with dynamic features like dynamic control flow, dynamic types, or impure functions. First, we could generate a graph that exactly follows the dynamic behavior of Python. For example, if we have a loop statement in Python, we may generate complex control flow graph operations. However, even though the graph execution can be correct, executing that graph would be very slow compared to the specialized version of the graph. For completely unrolling the loop, for example. In this case, however, the dynamic semantics of Python cannot be correctly preserved in the converted graph. To overcome such challenge and achieve correctness and performance at the same time, we use speculative graph generation and execution approach. For performance, we specialize the graph by exploiting the runtime profile information to make reasonable assumptions about program behavior. And for correctness, the optimization is done speculatively, and we fall back to the imperative execution if an assumption is broken. Let me briefly show you the overall workflow in Janus. Once Janus receives the input program, the program is first executed imperatively, while the profiler gathers runtime information required for making reasonable assumptions about program behavior. Then we speculatively generate a specialized graph based on the profile information. Running the specialized graph is likely to be valid over repeated execution of iterative gradient descent optimization algorithm. However, due to the dynamic nature of Python, sometimes it is unavoidable that some of the assumptions become outdated, so we must validate our assumptions. Janus checks every assumption, and if an assumption is broken, the system aborts the graph execution and falls back to the imperative executor and starts profiling again to generate another graph based on the updated context information. Now let me show you some evaluation of our system. As you can see with this ImageNet convergence graph on 36 GPUs, Janus makes ImageNet to converge 3.4 times faster compared to imperative execution. This speedup is similar to symbolic graph execution, but without modifying the original imperative program. And this is the normalized training throughput on a single GPU with various models with dynamic features. Janus achieves up to 47.6 times faster speedup compared to the imperative execution. And this is more than 96% of the throughput of symbolic graph execution. Yeah, thank you very much.
Super cool. Normally in the PL world, you don't think of symbolic execution as being faster. That's a great demo. And up next, we're going to hear about an operational model of schedules. Yeah.
Good afternoon. My name is Yongfeng. Today, Yuan and I want to present an operational model of Tensor Expression. Tensor Expression is relatively easy to start with to try around because it only involves a few instructions. But when you start stacking these instructions up, it becomes complicated very quickly. And we believe using this model along with some visualization tools, we can make it less challenging to understand and communicate with. So I'm going to start with showing you an example of debugging an error in Tensor Expression. And I haven't talked about the model yet, but I don't have time, so let me give it a try. Here we go. 7 lines of code. At the end, there is one schedule. Is this schedule legal? The answer is no. But the more important question is why and how can we fix it? Take a closer look. The first few lines defines 3 computations back to each other, and every computation dealing with a 2D tensor using a 2 levels of nested loop. The 0 rows are the outer loop, 1 for the inner loop. The bottom boxes are the computation, the loop body. Step 1, compute at. Move the entire loop of B under the loop body of C. So make C and B a combined loop. This is perfectly legal. Cache read. By definition, it inserts another computation between B and C, that's BL. That's quite obvious on the top, showing on the top. But what is less obvious is that the loop of BL sits outside the combined loop of B and C. So make data dependency showing on the top broken. So this is illegal. One possible fix is just to move BL and C so that B, BL, and C are within one loop, so we can restart the data dependency. Okay, so that's the example. As you can see, if I use these graphs as a language, they make it easier to understand these semantics and the correlation between these primitives. And it's also very useful for debugging, and we believe they also can serve a foundation or framework for people to discuss current behavior and the future works. So this is the model we are proposing. To capture the semantics of the tensor expression, we use 3 graphs. The data flow graph for the data dependency. Schedule tree is the current scheduling, and the interval relationship DAG is the evolution of these schedules. These are not new ideas. Actually, TVM earlier paper has similar or same definition of these graphs, and the schedule tree is used by almost every schedule language. But we want to bring this back to the community's attention because we don't see them used quite often in the documentation and the discussion. When we also believe using these models can make the spec of the semantics clear, that will make the foundation of TVM more solid. And also more and more target-specific support is needed, a new feature coming in, and this model can help both. Therefore, 2 days ago, Yuan made a post in the forum about a document. You can search for operational model to find this post. That's the top result. And this document is not a spec. Actually, we use this model to describe complex primitives, semantics, and some scheduling concepts. And these are things that we try to make them like stable. And we also use other formats like code snippets, examples, debugging points, debugging hints, and open questions for those things relative to implementation details. But these are in a less strict format to capture these ideas. We think they are important and interesting. So at the end, we'd like to contribute back to the community, and with this model, the document, we are also happy if there are similar solution or alternative solution for the same purpose. We have a tool called TEDD to visualize certain graphs. So some of the graphs shown in the earlier slides are rendered from this tool. We want to contribute that too. And after this talk, we appreciate you to look at the post and leave your comments and possibly answer these survey questions, right? Whether this is useful, are these graphs are well understood, will you use them, and can you help? The document is on Google Doc, and it's open for comments. So you can comment on topic, format, and content. And before I stop, so we are NVIDIA, and we are also hiring. Thank you.
Yeah, we'll definitely be looking at that in our next relay meeting. It's always great to have crisp models to explain how things work. So up next, it's a pleasure to introduce Yuan, who's going to be telling us about FireIron.
Thank you. Thank you. So this is an experimental scheduling language that we've been developing at NVIDIA for more than 9 months, and it's joint work with Bastian Hegdorn, Sam Elliott from UW, Henrik from Germany, and Ras from UW. So we started this work last summer in 2018, and it has a lot of input from many people at NVIDIA. Some of them are here. So basically the overview is that we need a hierarchical scheduling language to express GPU optimizations. And we want to get maximum performance that uses our storage hierarchy. So we have registers and shared memory. So Tensor Core added the notion of a fragment. Compute hierarchy, we talk about threads and blocks and kernels. With Volta, we introduced warps. We need to be able to make them explicit. We want to be able to reason about machine level concepts, and we want to make something that's suitable for auto scheduling and auto tuning. So dive right in. So this is a simple kernel on the left for a matrix multiply. And I've got boxes drawn around it. So basically it's a specification of a matmul. M and K are the sizes. And then there's a location of A, B, and C, which is global memory. And the responsibility in the compute hierarchy, which is the computation, is a kernel. So that's how we start. And that's the outermost box. And it's decomposed pictorially into this little diagram on the right-hand side. So I'm going to dive right in. I wish I had the time to give a longer talk. So basically, we go hierarchically down into this implementation to give you an idea that at the top level is a matrix multiply of M and K. Then we go at the block level, still in global memory, 128 by 128 by K, and then keep going down. And the bottom cartoon on the left to right shows you how it progresses. So quick overview of specification. So a specification of a matmul is the following. It says it's a kernel. A, B are the operands, and it specifies the sizes, what memory hierarchy, what element type, and what is the storage layout. Given a spec, you can do three things. You can actually substitute that with a handwritten microkernel that you got from somewhere. You can arrive at an executable specification, or you can decompose into smaller specification. So I'm going to go to the third one, which is the most interesting one. So we do a transformation from a specification to another one. Two major things, dot tile and split. There are many others. So let's look at tile. So what tile does is, given a matrix multiply specification, we're going to do a tile of 128 by 128. And that basically turns that into a specification, a smaller specification. So to solve that bigger problem, we need to first solve the 128 by 128. And that corresponds to putting a loop around the kernel. And we have to now figure out what the matmul 128, 128K will be at the block level. And we also added a refinement to the scheduling language that we want to give it to a block, thread block. Then there's another refinement or scheduling primitive called split, which takes a matrix multiply in this example and constructs an outer product. Right. So that's what we do. Then we have how do you move things into the memory hierarchy. So there's a load. We take a load, an operand, and we say move it to shared memory, and we specify a strategy. So the strategy in this case would be, for one example, we move from global to shared, and that is done collectively by a block. And then we synchronize, and then we do the matrix multiply as usual. So that's the specification. That's the implementation or the code generation on the right-hand side. Now to do tensor cores or WMMA or MMA, we need one more concept, which is fragment. So fragments are also part of this language, and that's what we do. So I don't have time to go into all the details, but the last slide here is we implemented this language, and we actually can get up to, we tested it on a large number of sizes against cuBLAS. And on certain matrix sizes, we can go from 1.5x to 2.4x faster. And we can represent this automatically. And with that, I guess I don't have time for questions. But please see us after doing the social. Be happy to answer any questions.
Yeah, perfect.
Thank you so much.
I am always excited for more ways to schedule. I want to know if we can automate that searching for those schedules. How?
Yeah.
Oh, perfect. There you are. Sorry. Perfect. Oh, and I just closed it. Just kidding. Okay. Now let's hear about ranking ads with TVM.
Hi, I'm Hao.
I'm Ansha.
And we're going to talk about how we made TVM work for ads ranking at Facebook. First, let's look at how ads ranking works at Facebook. So on a very high level, it's a very simple problem. When a user request comes in, we need to rank a bunch of ads and return the top 10 ads to the user, for example. But in reality, we have like we have millions of ads in inventory, and we serve like hundreds of models in production just for ads ranking. And ads ranking is like one of the biggest services in Facebook, and it's responsible for over 90% of our revenue. So we use different models to predict different scores for the ad. But not all ads are like processed by all the models, and also not all the models are served at the same as for each request. So looking at this in more details, we use both model parallelism and the data parallelism to speed up the execution, model evaluation. Each model runs on a single thread, and for each model, there can be also like multiple batches running at the same time to speed up execution. And in this case, like weights have to be global, and then they're shared between threads to save memory. But activations have to be thread local because they're running in parallel. And also, like we have to like release the memory of the activation proactively, like after each inference, to avoid running out of memory. This is like one of the special requirements of our production system, because we need to serve like so many models at the same time, and our scale is like huge. Some other production requirements including like dynamic batch size and a C++ only production environment. And we also need to work with multiple CPU architectures and make it work for both AVX512 and AVX2. Now I'm gonna pass it to Ansha to talk about how we make TVM work for ads ranking.
Cool. So for the high-level model architecture, we combine dense and sparse features to produce predictions for multiple different ads for a single user per batch. And this comes with really tight requirements for latency. For the sparse features, we feed them through an embedding lookup, and this is memory bandwidth bound, and this takes up the majority of the model size. The dense features, we feed through a couple FC layers, and we have interactions between them and the embedding vectors, after which we feed those through additional FC layers. And this subgraph is what we currently lower into TVM, and it's compute bound. Now for some of the integration details. We need to do JIT compilation since we don't necessarily know the input sizes ahead of time. That means that when a request comes in and it has an input size that we haven't encountered before, we kick off compilation of a new graph runtime. This means that for each model, we're holding multiple different graph runtimes in memory, one for each input size. This means that in order to prevent a memory blowup, as Hao mentioned before, we need to do some special memory management outside of the graph runtime, including sharing of activations and sharing of weights. For performance, we use MKL for FCs, since this matches the baseline operator implementation. And using this scheme, we get roughly 5 to 10% speed up, mainly from the fusion of the feature interactions and the FCs. However, runtime overhead eats into some of this speed up, and we have a couple different things that we can do to improve this. As some of you have mentioned earlier today, we can use Relay VM, which allows us to get dynamic shape support out of the box. For performance, we can leverage our large data to do auto-tuning at scale, and we can implement some high-performance, low-precision operators that will help us with low batch size FCs. And if we integrate embedding lookups as well, we're able to potentially lower the entire net, which will also help us. So that's all for us. Thank you.
Thank you.
This is exciting. First, I hear that every time I talk to Alexa, it's going through TVM. Now I know all the ads I see when I'm browsing my newsfeed also are going through. It's pretty great. Mix Marita, going to tell us about TVM on the edge. Please take it away.
Hello, my name is Kazutaka Morita from NTT, and I talk about TVM for edge computing from the perspective of the telecom company. In the 5G era, inference can be done in real time even if it is offloaded to the edge. And in this talk, edge means the MEC server, which is located in front of internet. Offloading inference to the edge has many benefits. In 5G, edge is a target of offloading, like AI chips in the device. So devices can use high-end hardware in the edge, and also low-cost devices don't have AI chips, but we can do a complex inference with the edge in real time. And another benefit is we can use data for real-time inference. And by sharing data with other devices, we can do inference with interaction among devices. These are examples of AI, and this is my team is working on. And it is very effective for offloading to edge. And occlusion is important because it is necessary to move virtual objects naturally for AR, but it needs a lot of inference tasks. For example, plane detection, segmentation, and mesh data generation, and so on. And if there are many objects in the images, devices will be very busy. And an example of using data is point cloud. We can create AR image like this by doing inference with point cloud data from cloud and captured images from AR glass. This is the idea of edge computing platform with TVM. We think of using TVM with edge device SDK and generating inference runtime with TVM. TVM generates not only device runtime, but also edge and cloud runtimes. Each device do inference dynamically based on device and network status. For example, runtimes do inference only on the edge when device is busy, and only in the device when network is not available. And when latency is not so important, it is also good to offload to the cloud beyond internet. And these are features we'd like to add to TVM for edge computing. By adding offload support to heterogeneous runtimes, we can offload operators of the graph to the edge with annotation. And I think it is also interesting if TVM could support which operator should be offloaded to the edge. And the second is dynamic runtime. We switch accelerator based on device and communication status. And I think using of this feature from external scheduler. And smart NIC support is also important for real-time inference on the edge. And we are still working on POC evaluation for edge computing. So if you are interested in, let's collaborate and work together. Thank you.
Nice work. Okay, let's see. What are we up to? Cody is going to tell us more about auto TVM efficiency. Yeah.
Hi, this is Cody from AWS. So today I'm going to show you how can we improve the auto TVM efficiency by schedule sharing, which brings another angle of an idea about how to improve the efficiency other than just improving the tuning algorithm. So this is the motivation. If you ever used the auto TVM, you must be very familiar with this. This log and flag. 2 points here. The one is, this is the example of tuning the MobileNet V2 on NVIDIA V100 with only 500 trials for each op. So you can see we have 31 tasks in total, including comp2D and depth-wise comp2D operators. But only with the 31 tasks, with the 500 trials for each, we still need 40 minutes on average for every task, which means 19 hours in total for only tuning this model from end to end. However, on NVIDIA V100, you usually recommend to tune each op for 3,000, even 4,000 trials. So which means this time should be doubled by many times. So this is pretty tedious. And how can we improve this without thinking about how to improve the tuning algorithm? So here's an interesting observation that we found during this period. We found that AutoTVM actually tunes every task in the model from scratch, which means when you are tuning the second layer, you didn't take the experience from tuning the first layer. That's by default. And which means some high quality schedules from some tasks in the model are very similar, because you can imagine the ops, all the Comp2D ops from a model may share the similar image size, kernel size, or stride and padding. So one of the proposed solution here is that how can we, if we can only tune some representative tasks and share their best schedules to others, so that we can save a lot of time for tuning every layers. So here is the initial proposal for achieving this. And the idea is we identify 2 tasks that can share schedule to each other if their tuning space are very similar. So approach is here. So first we can cluster the task with the distance metric. This metric can be varied. For example, I have experiment about, for example, k-means or the similarity rate between two tuning spaces. So whatever the metric you use, after you clustering the tasks based on those metrics, you can identify the centric, or we can say the representative tasks in each cluster, and only tune those few tasks. And after that, we apply the best schedule found by those representative tasks to all other tasks in the same cluster. So this is a very simple idea, and there are some initial results. The results are actually very encouraging. We can see that I selected 7 models from grown CV model zoo. So they are all CV models. We can see we have some MobileNet, ResNet, and we also include some image recognition like YOLO 3 or SSD models. We tune those tasks, selected tasks, usually select 5 to 7 tasks based on the model. And we tune them from 300 trials on NVIDIA V100. And then we apply those to other tasks in the same cluster. By doing that, we can achieve on average 84% performance with only 28% tuning time. So you can see the use time here in the second from the right column shows how many times we used for achieving how many numbers of performance in the very last column. So this is the initial thought and the idea to share with you guys. So, and the RFC is also here on the TVM repository. So welcome to participate and share your ideas to make this idea better. Thanks.
Yeah, it always makes sense to avoid reinventing the wheel. I'm curious what happens when you have other like NLP models. It'll be really interesting to learn. So up next, I think we're going to learn about risky vectorization or something like that. Yeah.
So I'll try to give the update on the TVM on RISC-V with Cindy computation. So this is joint work with the NTHU and the PTL group and NDs. This one. Okay, thank you, thank you. So this file with 2 kind of Cindy in that specification. One is the superword Cindy with V extension, and the other one is the subword Cindy, known as P extension. And we currently have both of the reference design from TVM for the RISC-V with P and V extension. For the P extension, they don't have the floating point Cindy, so we have to do it by the integer or with the fixed point. Since the fixed point is well known in the DSP and sort of NVIDIA design, so we use the fixed point in our implementation. So we now put a different design in the RPC in the fixed point type. So basically, fixed point type is basically you have a binary point position, so the integer part and the fraction part. Because the fixed point is well used in the DSP community, so now they have some high-level language specification from different sides. So for example, we have like AC fixed point by MetaGraph, now as Siemens, and also our early proposal to Kernel OpenCL fixed point feature set. And basically, proposals are slightly different, but they have a common thing that they ask the compiler time with the type information. So the compiler can know the binary point position for the variable. In that, the compiler can use the type information for possible optimization and tuning. So for our case, in the RISC-V implementation for the subword SIMD extension, we extend the concept of the auto TVM to have the auto fixed point selector. Hope to have to choose the best binary point position and use the polynomial regression prediction model. So for example, when our selector come out in the original implementation, the developer in our group, they actually find out the 12 setting the binary position of 12 is pretty good for the Alice snake with the CIFAR data set. And by the time the auto-tuner come out, actually it's really surprised the tuner find out the setting the binary position at 13 bit, at the 13 bit actually gives the better accuracy. So the tuner actually has a systematic way to find the best binary position. So it's actually better than the intuition from the developer. And currently, our implementation is use the Yongfeng selector that gives the Yongfeng selector for all the layers. But we hope to further extend to not just select the binary position, but also width, and also try to have different, for the different layer, we might choose different binary positions. And for the superword extension, for the V extension, the current implementation is a modification for the two parts. One is from TVM and one is in the LVM. In the TVM RISC-V codon will lower the SIMD into the SIMD intrinsic to LVM. And the LVM backend will generate SIMD instructions. In that, we actually need to have a better schedule to provide a large loop index space for the beta paradigm, because the RISC-V extension allows a wide vector. So a better schedule actually is needed to accommodate the beta paradigm. And we only do the TVM optimization. We get the performance improvement in the blue bar. But because the LVM compiler we use is from LVM 9.0, from the official trunk, and that for RISC-V is actually quite new. So there are a lot of tuning needed for the LVM optimization. For example, we have some tuning for the LVM compiler. For example, the RISC-V V extension, they allow flexible vector. For example, in the runtime, you can set the vector width and also the basic element size. And that for different layer loop, they might be different in the vector. So in the TVM loading and also LVM implementation, you will see a lot of different settings for VSet VL for vector length. And we perform a partial redundancy simulation to remove all those redundant parts and can reduce the redundancy. And also better utilize the multiplication and add resource and better initialization in the implementation. So our experiments on the Sparse simulator and compare with the SIMD with both 32-bit and no SIMD, and with the original spec 0.7. So So I'd like to thank the AWS team to help to guide our AI model validation flow. And we also have some reference for our more detailed technical part. Thank you.
I'm really curious to see how things work with that limited dynamic range. But up next, we're going to learn about optimizing sparse graph kernels with TVM. Okay.
Hello everyone, I'm Yuan from Cornell. Today I'm going to present my internship work at AWS, which is optimizing graph kernels with TVM. Graph neural networks are getting popular in recent years as a promising approach to handling learning tasks on graph. One application, as we have seen, is to improve the cost model in AutoTVM. As we know, the computation on graph is sparse. So here we identified two key kernels in graph neural networks. First, message passing is doing sparse dense matrix multiplication, SPMM, or more precisely SPMM-like if we use a customized reduce function. Here, the sparse matrix is the adjacency matrix of the graph. The dense matrix is composed of feature vectors, which are associated with vertices in the graph. The second kernel is SDDMM, sampled dense matrix multiplication, which is to multiply a dense matrix with another dense matrix, and then do an element-wise multiplication with a sparse matrix to get sparse output. This kernel is required for calculating dot product attention. The challenge here is that these sparse computation kernels are not well handled by existing deep learning systems or existing graph processing systems. Existing deep learning systems have very limited and inflexible support for sparse computation. They typically rely on vendor-provided libraries, such as MKL on Intel CPU or cuSparse on NVIDIA GPU. Existing graph processing systems are more flexible and can easily express these sparse computation kernels. However, they are designed for traditional graph applications, such as PageRank, where each vertex is associated with a scalar instead of a feature vector, as you find in graph neural network. So they are missing optimization opportunities on this new feature dimension and not able to deliver very good performance. In this work, we explore optimizations on the feature dimension. Specifically on CPU, we do feature dimension tiling to improve cache utilization, and we combine feature dimension tiling with existing graph partitioning methods to further improve the performance. On GPU, we specialize parallelization strategies for computation patterns instead of using a fixed schedule as you find in existing graph processing systems. Here shows some preliminary results we get on CPU. We do the experiments on AWS C5 instance. The data set is Reddit, which is commonly used in graph neural network research. It has 200,000 vertices and 100 million edges. We compare TVM with MKL, which is Intel's official library, and Legra, which is state-of-the-art CPU graph processing system. The figure on the left shows the result for SPMM running on single thread. As we can see, TVM is faster than both MKL and Legra. The figure on the right shows the result for SDDMM. As we can see, TVM is 4 times to 6 times faster than Legra, while MKL doesn't support this kernel. Okay. So now we are collaborating with DGL team, Deep Graph Library, to do some integration and end-to-end testing. On the front end, we use the message passing programming interface from DGL. On the back end, we offer these highly optimized sparse kernels written in TVM. I want to mention that the current implementation is using IR Builder. We expect that in the future, these optimization techniques can be abstracted into schedule primitives. For example, we can introduce a sparse split schedule. I want to mention that this would rely on infrastructure to represent sparse tensors in TVM. We noticed that there are ongoing efforts from UW to build such an infrastructure. I look forward to collaborating on this effort. Finally, I want to thank Jali for helping with benchmarking, Andrew for contributing the blocked sparse kernel in TVM, which greatly inspired this work. I also want to thank Zihao for discussing DGL integration and Lo Yuan for discussing GPU optimization. That's all. Thank you.
Super cool. Sparse is everywhere. Okay. And I guess, Alvaro, yeah, you're up next.
Yes.
Excellent, okay.
Hello.
Yeah. Well, as the slide says, a big hello. We're a new company. My name is Abelardo Lopez. The company is Latent AI. You can think of us as the people that are developing the tools that talk to basically the designers of the neural networks, right? So our company, the reason why I put this is as just as a context, we develop tools for efficient and adaptive AI. But again, see us as someone that comes from the other end, not the compiler and not the processor, and we're coming from the applications, right? So our goal is to develop these efficient tools that target edge devices. So we are concerned obviously about memory, power consumption, and all that. We're a very early startup. We started, we were founded in December 2018, but started on June this year, late June. So we had several goals with the TVM project. We started, of course, with our tool set. We are developing tools such as, quantization, pruning, gating. All this occurs usually outside of the compiler infrastructure. So we are very new to the community. Actually started interacting with the community in September, mid-September, late September, so it's very, very, very new. We wanted to integrate TVM to test some of our edge cases, right? So we have our tools, we want to evaluate how they work on edge devices. So we said, well, let's use TVM, right? So we learned a lot of stuff. We want to share that with you today. And also we want to engage the community, right? We found a lot of improvements that are out there. Some of them have already been mentioned, such as, improving the documentation and whatnot. But in particular, what I want to talk about is these three particular steps, right? So first of all is we looked at the examples and we realized that they're in non-standard way. So there's like, this particular example does this, that one does that. So the first step that we did is we took the examples and created a script version of each of them. And those scripts are very structured. So the reason why we did this is we wanted to have a command line interface to TVM. And that's something that already was mentioned in the morning. We thought it's very interesting because if you are a designer, you want to iterate over different versions of your parameters. And right now on TVM it's not very amenable to do that, right? If you have a command line interface, then you can iterate, change parameters, do that programmatically and systematically, so you don't have to stay in front of the computer the whole time. So we developed that command line interface. We're open to putting that into a request for comments because what worked for us may not necessarily work for all of you. Just to give you an idea, we use the model parameter, input parameter, the output, the shape. Also, if you're using floating point, if it's quantized, not quantized, and then we can start changing and playing with those parameters with scripts. And then we also developed some demos. Again, this is with our technologies. I was going to show it to you, but I only have like 2 more minutes to go. So if you like afterwards, I can show you the demos. We have one on the cell phone, the other one on a Raspberry Pi. Pretty nice demo. So what we want to do, and I already started doing this, is starting to collaborate with the TVM community, especially sharing what we learned, especially the scripts I think would be useful. More examples are usually good. You also want to open this request for comment for the command line interface. Again, the reason why we did that is we want to separate the compilation versus the inference, right? You want to, compile, look at the binaries that generated. We actually run some interesting experiments that unfortunately didn't have enough time to put them in here, but again, we can talk about it later. About what happens, for example, with parameter sizes as you sweep around with different compiler algorithms like XGB or random. If you iterate, increase the number of iterations, the graph size changes, which is sort of interesting. So, so we want to explore collaboration. We also, again, this is our first meeting, so we want to keep going back. And again, feel free to contact me or Mark, which is back there, so we can talk in more detail. Again, I didn't include all the details here because I think this is more amenable for a request for comment. But I want just to let you know that we're here to help the community. Thank you.
make sure to check those demos out in the social hour here real soon. Oh no. I got it, Zach. Okay, up next we're going to learn about analysis from Gus.
Hi, everybody. So I'm Gus. I work here at UW in our sample lab. And this past summer at Microsoft, I built a program analysis framework on top of Relay. The program analysis framework basically helps you write simple data flow analyses over programs and then compose their results into human readable formats. And when I came back to UW and wanted to incorporate this framework back into Relay, I discovered that there wasn't really an appropriate place to put it. And this surprised me because looking around Relay, I saw plenty of analyses of different shapes and sizes, from simple static analyses like these to big dynamic analyses needed for things like quantization. And what I discovered was that there wasn't really a place for my analysis framework because there is not a whole bunch of analysis tooling in Relay at the moment. These analyses are built in kind of an ad hoc fashion. They're built from very basic analysis tools. And there's no underlying, no backing analysis framework that they're built on top of. This means that there's no Relay-sanctioned way to build program analyses. There's plenty of tools in Relay for building analyses, but they're all fairly basic, which means that every analysis you build has to be built from these very basic building blocks. This lack of an idiomatic way to build analyses in Relay can lead to a lot of problems. So first of all, there could be a lot of duplication of effort. Every time somebody needs to build an analysis, they'll need to rewrite the very basic analysis tools. It can also lead to a high barrier of entry for new developers who, every time they want to build an analysis, will need to build from very low-level API calls. And then also, for large and complex analyses that are often just built by one or two authors, these analyses can be much less readable and maintainable because they'll be relying on very, very low-level primitives and will be built completely from scratch every time. So not only is this a big problem, but it's also something that the community wants. Just recently, Marissa posted an RFC for analysis in Relay programs. And in addition, just yesterday, somebody posted an RFC for data flow analysis over TVM IR. So clearly there's a desire from the community to have a few correct ways of doing analysis in Relay. So let's take a look at an example analysis and see how it might be improved with an analysis framework backing it. This simple static analysis simply finds the values attached to variables in Relay programs. It's used in the dead code elimination pass, but you could also imagine it being used to build more complex analyses. It has use far beyond that pass. But before it can be used outside of that pass, there's some problems that it has that could be fixed by an analysis framework. So first, it needs some documentation so that it's more understandable what it's doing. Beyond better naming and code commenting, one really great way that this pass could document itself is by relying on a well-documented analysis framework. Number two, it needs a standard data interchange format so that it can be composed with other analyses and pass its data on to other analyses in an understandable way. This is something that an analysis framework could standardize. And lastly, it needs to be discoverable and accessible by all developers on Relay. And a good way to do this would just be to have all analyses be registered with this central analysis framework. So in the end, what do we want out of a framework? Well, first, we want a framework that supports many types of static and dynamic program analyses and doesn't limit us in the analyses that we can build. We also want it to be quick to write new analyses, especially for new developers who are coming onto the project. And lastly, it should promote composing analyses together so that we can build complex analyses off of simple building blocks, and those simple building blocks should be reusable. So the framework that I built this summer at Microsoft was a rather simple attempt to achieve many of these goals for simple data flow analyses. And you can take a look at it. It's on Microsoft's GitHub. I also have a demo of using that analysis framework on my branch of TVM. And looking forward to the future, so the whole point of this lightning talk was to call attention to the need and the community desire for better analysis tooling in Relay. So if you have any strong opinions or want to contribute anything to a push for Relay analysis tooling, please go ahead and drop your comments on this RFC. This is not my primary research interest, but I'm happy to push for better relay tooling and happy to drive this discussion forward. Thanks, everybody.
Can never have too much program analysis, that's for sure. All right. So up next, we have a spicy talk. TaskTabasco? I don't know,
Maybe.
spicy talk?
Yeah.
Oh, yeah.
It's TaskTabasco with a P. Okay. I will talk about the task parallel system composer for FPGAs. It's called TaskTabasco. And actually, the aim of this is, Louis called it tomorrow morning the Cambrian explosion of hardware backends. And this is more or less yet another hardware backend. Here's the Amazon Web Service logo because this is one of the last backends we added now to the TaskTabasco framework. And the idea behind it is that you can use this framework to build for FPGAs a complete system on a chip design from high-level synthesis kernels or custom HDL cores or custom IPs, whatever. It allows design space exploration and allows to explore the best parameters for your kernels and system composition. The main advantage is that it supports Xilinx platforms. Up to now, you may be wondering what this has to do with VTM. And the main idea of it is that you use the VTA core as one of those kernels which you instantiate with TaskTabasco. As many things here presented, this is available as free and open source software. In the end, you see a link on GitHub. The design flow is that you can instantiate on this system the ALS cores. This is, for example, a VTA kernel. And this goes through the regular design flow by using the HLS compiler. And TaskTabasco is then used to instantiate the FPGA design, which afterwards get the standard low-level synthesis with place and route afterwards. Here in the bottom, we see such a command line, how you would instantiate some kernels. And its example, you see here the VTA kernel name. And it's actually, in this example, instantiated twice, together with some other kernel, which does some other task. A Sobel filter is this in this case. And you say on which platform and what your design frequency is. The general architecture, and this is the main feature of it, is that that TaskTabasco provides all this red-marked environment and infrastructure available on the platform. And the idea is that the user, which now wants to instantiate different kernels, don't have to care about this infrastructure. He just says which kernels you want and how many of them, and then these are instantiated as processing clusters, are they here called on the graphics, and they communicate with the rest of the platform with a DDR controller or with a BRAM available to everything via infrastructure which is provided by TaskTabasco. In our example, this cluster is VTA, and here we have, I don't know if you can see it, yes, the elements which are usually instantiated by VTA. He uses a load module, a fetch module, compute module. They are all described in C, C++, and then translated via Vivado HLS. The regular TaskTabasco stack looks like this. We have on the bottom different hardware platforms which are supported by the device drivers, and the communication is done via a platform API. On top you have a TaskTabasco API, and above it you have the usual user software interacting with the platform. In our case, this would be TVM and VTA. And in VTA, just the regular tasks, function calls, which are used to communicate with so far used hardware are replaced with TaskTabasco calls and allow transparent communication for the user without further interaction by them. There are several platforms we support. You see, it's just more the regular VTA support is just the ping board at the moment and the Ultra 69. As far as I know, I think there are some better platforms which are supported more or less, but I don't know if there is plans to do more because now the transition to the chisel backend is done. But I guess if the interfacing is similar to the old VTA, there is no problem with instantiating a chisel kernel in TaskTabasco. You see, we have a plethora of platforms, and the newest one is the AWS F1 instance, and you don't have to care about anything. So far, you used one of your ping driver backends, for example, and now you just use TaskTabasco as driver, and TaskTabasco can now be instantiated on any of the other FPGA platforms, and you can run it without further ado, and it allows even more options. So far, we just instantiated the small accelerator from VTA, which has a very limited size. This is a gamma array. But as we have now the possibility to explore the space and the available resources of much bigger, much larger FPGAs, we have now the chance to implement bigger arrays or instantiate multiple VTA instances on one FPGA. There we have at the moment several work in progress projects where we try what are the best solutions to utilize all resources available on such big FPGAs. So finally here the promised link to the GitHub resource of the TaskTabasco. Feel free, download it, try it out. Even if I sell it to you, or I try to sell it to you, it costs nothing. And I think I finished now. I have some more slides, but regarding to the time, I skipped them, and I think that was it. Maybe I should mention that we are also hiring. So if you are if you are experienced hardware developer and searching for a new job in Germany, you can contact me. So that's all.
It's really compilers all the way down. Okay. All right, up next, Mateo's going to tell us about compiling classical ML pipelines.
Thank you very much. Hi, everyone. So what I'm going to share here right now is an experiment that we have been doing in the past few months at Microsoft. And basically, the idea is really simple. Is try to compile classical ML operators into tensors. Why we want to do that? Basically, yeah, as you know, we have Onyx runtime, of course, TVM, and we have all this what I call prediction serving system that are basically helping in kind of speeding up your inference job. But the problem is that they mostly focus on neural network. But neural networks is not machine learning in general is not just neural networks, right? So we also have other type of algorithms. And the problem with this other framework, what we call classical machine learning, is that each of them, basically there is no unified system for doing inference on them. And each single framework, they have their own inference infrastructure. And of course, you cannot like share optimization and these all kind of things. And why are we interested in classical ML? Well, because if in practice, classical ML is still used a lot, both in industry and in general, in general by a lot of data scientists in practice. And this is a Kaggle survey from 2017, but we have evidences that this also hold now in 2019. So the question that we want to basically answer with this experiment is, can we compile classical ML pipelines into tensor computation so that we can leverage neural network systems such as TVM? And if you're able to do this, basically you're able to exploit all the available optimization that all of you guys are working on, and we get hardware acceleration for free, and then we get a lot of reduction engineering effort. And I put an hummingbird there to remember that this project is called hummingbird. So what I'm going to do next, so basically every time that I'm giving this talk or I'm sending a paper on this topic, all the reviewers were saying, okay, this doesn't work. So what I'm going to do for the next slides is, instead of explaining how we do this, I'm going to show you some number. So we basically got 4 different data sets. These are the characteristics, and then we got three models, random forest, XGBoost, LGBM, and then we used as a target for our compilation, we use a PyTorch, a TorchScript, Onyx, and of course TVM. And in this experiment, we should just batch inference, both on CPU and GPU, but the same result basically hold also if we want to do just a request response inference, so one single CPU and one single record. So here I'm going to plot like 3 tables, one for each algorithm. So the first table contains basically the random forest numbers, the second table the XGBoost numbers, the third table the LGBM numbers, and then we have the different data sets, and then we have the different targets. So if the targets start with HB, this is our compiler output. So it would be HB PT will be hummingbird with the PyTorch, and then TS is for TorchScript, Onyx, and TVM. Okay, so let's start to see some number. So we just started with the regular scikit-learn API. So we train the random forest, XGBoost, the LGBM, and then we use OnyxML to try to see how is the Onyx runtime working in this case. And here we see that basically 11 times out of 12, the scikit-learn is actually faster than OnyxML. This is because OnyxML is more optimized for single request response scenarios. Now, let's see for the others. So if we start to then use our hummingbird approach to translate the trees, we basically, it looks like it doesn't work. So in the worst case, we got a 7x, we are slower 7x, and in the good case, we are like 50% slower than the direct implementation, the baseline implementation. But now if you look at the TVM, now we got like, with TVM, we have 11 times faster over 12, and in the worst case, we are around 50% slower, and in the best case, we saw that we are 3x faster. And this is just on CPU. But of course, we also support GPU now, because we can translate it to this runtime. So, and this is where it's getting interesting. So if we run GPUs, already with the TorchScript, we got around 20x speed up compared to XGBoost in this case, and up to 11x speed up. This is the maximum we can get. With TVM, we got other like 2 or 3x improvement on top of that. So we are in the worst case 60x faster, and in our best case we are 200x faster. So a couple of months ago at NVIDIA, they open sourced this forest inference library. And when we saw the open source, they said, okay, no, they already want to do the same things that we were trying to do. So we tried to run an experiment against them. And the support is still limited because they only support XGBoost and LGBM, and they don't do multi-class classification. But still, we are 2x faster in the worst case, and in the best case, we are 7x faster. So basically, we are faster than custom implementation. And we don't support just trees. We actually support around 40 operators right now. And we are doing benchmarking for all of these operators to see what we can get. I don't think I have time for the conclusions. So thank you very much.
Great lightning talk. I always love when that like TVM column gets revealed because you always know, right? The speed ups are going to be incredible. All right. Last but not least, we're going to learn about DRAM access reduction by node fusion. All right, take it away.
Okay. Hi, I'm Jeong from Tsinghua University. I'm going to introduce the DRAM access reduction by node fusion with TVM. This research is co-worked with E3. So here is the motivation. For the mobile and cloud applications, the energy efficiency is one important factor to DRAM computations, especially for hardware accelerators. To save energy consumption, the simplest way is to buffer the data in SRAM as possible. Because the DRAM, a typical DRAM access is 50 to 100 times more than SRAM. So here is a table to show each energy, the data access energy of each memory component. The register usually takes picojoule to read data, and SRAM usually takes 4 times more energy than register. The DRAM takes 250 times more than register. So in order to reduce energy consumption, we use node fusion to reduce DRAM access. So here is how TVM performs its node fusion. TVM have a simple node fusion which merges the element-wise operators into convolution. Take the mobile net as example. Mobile net is comprised with convolution, batch node, and ReLU. Each of the operator has an attribute to indicate whether it is fusible. You see here, our element-wise fusible, element-wise. And then TVM will fuse them into a TVM OP. Each of the TVM OP contains a subgraph to share the intermediate data by SRAM. So here is our version of node fusion, which merges multiple convolutions. The left part is the data flow of 2 convolutions without node fusion. So you can see 2 separate convolution for loops here. And the right part is the fused data flow of 2 convolutions, where the first convolution is computed inside the second convolution. So the output data of the first convolution can be reused in the SRAM. So this is our experiment settings. We run our experiments on an Iris-like architecture, which includes a 256 megabyte DRAM, 108 kilobyte SRAM, at 12 by 14 PE. And we run AlexNet as our workload. And due to the hardware limitation, only convolution is evaluated. So here's the result. We compare the timing, and energy and their production with and without node fusion. And the result shows there's 23% reduction in energy and 60% of speed out because we read data from the well-partitioned SRAM, which is faster than DRAM. So overall, the energy delay product is reduced by 40% by our node fusion. Thank you.
All right. Well, thank you very much. Everyone, this was a fantastic day. So here's what happens. We do have a reception set up. I was confused. Apparently we were too big to hold a reception here. We're holding a reception on the atrium of the Allen Center. You just have to go down, cross the street, and go to the Allen Center. There's a big open space there, so we don't have to keep bumping into each other to grab food, okay? So it's super easy. Just go down to the atrium of this building, leave, cross that street there, you see the Allen Center. You go from the Bill Gates Center to the Allen Center. You see the connection there? And there's a little bit of, yeah. All right, cool. Thank you all. This was really fantastic. Very nice meeting you. You want to join us at the reception there?
So I'm leaving for the